All right, this is where I go, since we're now recording. Welcome to the Maths 1A Revision Seminar. My name is Nicholas Crouch. I work in the Maths Learning Centre. I'm here to talk about some things. We've got some list of suggestions, which are hopefully up on the board. I'm going to, there's a few, but we've got 8, so that's 7 people online. So for the people online, feel free to put a comment in the chat for things you want to ask. I'm going to go over it's all right to ask me questions. The joy of having me here in front of you live is you can ask me a question. All right. So makes my life easier if you ask me a question, because otherwise I'm sitting there going, I don't know, what do I think they want to know today? All right. And one of the things you will learn, back when I was working for the school of maths, my favorite thing to do in the first seminar, workshop, lecture, or whatever, we go, no, I do like the sound of my own voice. I will to talk to the same talk. You guys want to get me to talk about stuff. You can get my opinion on Donald Trump's management of the USA at work, his trade policy, his managing immigration immigrants. Happy, we'll talk. Not qualified. Maths on the other hand, I did lecture for the School of Maths. So I do know what I'm doing when it comes to doing that sort of stuff. All right. So it is kind of what I do. So let's see, we've got 19, we've got that's another 5, 24, 25 there, 7 online. Woohoo, we'll call that 32. Sweet. All right, we actually have an official number for who's here. All right, so we're going to start with spanning. So the reason I said spanning, subspace, basis, they're all talking about the same sort of things. All right. So oh, okay. Okay, sure. Good work. All right. So the other thing to say is my supervisor, when I was doing my research, was going, your IQ drops by about 20 points when you have to sit up in front of a class and give a class, right? And it's true, sadly. And so little things like, is the thing I'm doing on the screen is quite often a thing. So don't be shy about going, Nick, you're an idiot. Change, adjust where the camera is, all right? Because while I can see it, I'm not focusing on the camera, I'm focusing on the thing that needs to be said about whatever it is we're talking about. And the last thing I probably should say is all of the revision seminars that David and me have done over the 16 odd years that we've been doing stuff at the Maths Learning Centre are available on our website. All right. So if you go, hey, I didn't get to the seminar, what am I doing? The answer is you can look up the seminar. This one will be online sometime tomorrow, probably. So, if someone was going, if you're going, hey, what did Nick say about that? Then you can look that up tomorrow. But, or you can look at some of the other things we've talked about, because we have talked about all of these things. Not all of the seminars are there because either we decided they were rubbish, the recording didn't work, the university deleted them for us because despite asking them not to, they did it anyway. I don't know, not bitter about it at all, just in case any of you are wondering. So yeah. All right, so spanning. Spanning. All right. So when we think about spanning, spanning is just shorthand. All right. All right. Set of all linear combinations. Had a very annoying first year tutor. Every time he said the word span, he would say set of all linear combinations. Now, unfortunately, I can't hear the word span without saying in my head, set of all linear combinations. On the plus side, it's a very useful place to start, all right? So when we say span, all right, we're trying to, a lot of things we're going to do, because we want to be precise about how we talk about things, All right, we need to be quite exact in mathematics about how we talk about things. This is a way of saying this is exactly what we mean about this, all right? But to expand it, to use all the words every time is just tedious, all right? And I would have to give you like 3 lines just to describe the thing I'm talking about. So we use the word span to sort of condense the amount of words that need to happen. All right, so back when I was an undergrad in your very position, I was like, well, what the hell is span? I don't get it. All right. And the first thing I'm going to say is that is because there's really not that much to get. All right. It's a set. So a way of describing a set. All right. So linear combination. X is a, need glasses. Some vectors. So we can say, if we're saying it's a linear combination, we can literally write it as a constant times each one of these vectors. All right. Not very exciting. Okay. Where do we use span? So because it's actually basically notation, there's sort of some mathematical grammar around it. So if I say span, I have to say it needs to be followed by a set of vectors. So if I'm talking about the thing is blue, I need to specify the thing. And so the thing that spans is a set of vectors. Okay? And so that's how we need to remember to talk about it. So we're going to give you a set of vectors. I'm not going to go on too much about span because it's a bit boring. When I say X is in the span, though, I mean X can be written as a linear combination. And that's the thing you do, all right? If you do not know what to do, but it says X is the span of these vectors, X can be written like this. All right, sure. I'm a big fan of, you don't have to know how this argument is going to end. You almost certainly do know what the first thing you would do. All right, so if I'm asking you to show these vectors span, you kind of go, oh, okay. Well, anything that's in this set must be a linear combination. I'll try it out. What does that mean? So subspace. I'm going to kind of leave that there for span because we're going to come back to it. We're going to play around set subspace, spanning subspace basis. All right. So subspace. Subspace. All right. All right. Everything comes in threes. And for linear algebra, that's more or less true. So first thing, so again, a subspace is a set of vectors. All right. So they're vectors in a larger space. We'll go, hey, these are vectors in Rn. All right. 1. W contains 0. All right. Everybody loved that. So it's got 0 is kind of like the center, if you like. All right. So quite often we will define where we are as the center. All right. If you talk to astronomers, depending on what they're talking about, they may define Earth as the center or the sun as the center or the supermassive black hole in the middle of the Milky Way as the center, depending on what they're talking about. We can redefine what the center is, but if it's a space, it's got a 0. All right. So we're going to say, oops. All right, closed under multiplication by scalar. Literally, I can take any element in there and I can multiply it by any real number. If my handwriting's too crap, please tell me. My handwriting is terrible, but hopefully while I'm talking and writing at the same time, we can do this. So, and this is this idea that there is no end. So this includes, there is no end. If I have a vector and I go any number multiple of that, that number can be pretty damn big. And, you know, so I can literally go in that direction as far as I like, and I should still be in my space. There is no end to this space. All right, and again, closed under vector addition is a thing where we go, hey, we can do this. All right, now, the secret to subspaces is firstly remembering these things, but secondly, kind of knowing what is a subspace. All right. So we don't go through and check all of these things every time we see something. We go probably is, probably isn't. All right. So the first step when we're coming to is this a subspace? Is do I think it is? All right. So if I was to give you a set, I maybe give you a set of X in R3, say, such that we'll call it, we're going to stick with W. W is equal to the set of X in R3 such that X plus Y plus Z is equal to 0. All right. I want to keep it simple because I don't want to have to do tricky things by doing this. All right. The amount of tricky calculations I want to do is little because I want to just illustrate. What would I show now? Do we think this is a subspace or not? All right. I feel like the answer to this is yes. This is a subspace. All right. So my zero vector would be equal to 0, 0, 0. If I go 0 plus 0 plus 0, 0, it would be equal to 0. Tick, contains 0. Woohoo, everybody happy. Now I have to get creative. All right, so x1, y1, z1 be in W. And so if I'm going to go down this path of trying to show something is a subspace, I want to go, I want to take an element in there, arbitrary element. So when I'm showing it is, I have to show it's true for all X. So if I put numbers in here, it's not going to help me. It's going to show a specific case. It's not going to show that it's always true. So it's really important that I choose a particular thing. And so because I'm saying it's in W, I'm going to be specific about what that means. That's like X1 plus Y1 plus Z1 is equal to 0. And so when I do K times my vector, X1, Y1, Z1, then that's just going to be K X1, K Y1, K Z1. All right. Does it satisfy my, is it in my space? I've got to check this. So I'm going to do K X1 plus K Y1 plus K Z1. All right, I'm not going to say it's equal to 0. If I say equal to 0, I'm sort of saying the thing I need to do. Have I gone off the screen? Yes. Thank you. Well done. All right. So I can't say it's equal to 0, right? I want to show that it's equal to 0. And so I can't just whack equals 0 at the end, even though I'm fairly confident it is. I'm going to go is equal to K times X1 plus Y1 plus Z1. All right. But that's going to be K times 0, because I've assumed that's equal to 0. For that X to be in the set, well, it's equal to 0. Therefore, K X is in W. Woohoo! All right. So it's tedious, right? Showing something is a subspace is tedious. But that's what you've got to do. Like, if we ask you to show that something is a subspace like this, then we need to go through all of these things. All right. So the last one would be, I'm going to take a different one, x2, y2, z2, being very creative. And I'm going to do plus x1, y1, z1. And that will be equal to x1 plus x2, y1 plus y2, z1 plus z2. And so all right, so we're going to check if it's in W. So we're going to go x1 plus x2 plus y1 plus y2 plus z1 plus z2. Again, I'm not going to say it's equal to 0. I'm going to do some jiggery pokery. X1 plus y1 plus z1 plus x2 plus y2 plus z2. And then I'm going, oh, that's 0 plus 0, because I've assumed these things to be 0. Strictly speaking, I should have done a little bit here where I've said x2 plus y2 plus z2 equals 0. All right, because that's what it means to be in W. And then we go, all right, 0, which is equal to 0. All right. And so therefore, all right, close to the vector addition. Woohoo. Okay. And therefore, W is a subspace. All right. So that's what you have to do to show them. Now, so there's a bit of a thing. All right. There's a bit of a thing. I'm going to generalize this thing here to go. You might be going, oops, off the screen. Thank you very much. All right. So this thing, you maybe not, maybe your first thought wasn't, hey, that looks like the system of a homogeneous system of linear equations. But you can sort of, if I say it is, you can sort of go, yeah, okay, it only just qualifies. It's really playing fast and loose with the concept of system. There is an equation there, but equal to 0. But it is, that's what it is. And so we're going, hang on, what other things have we been asked to show are subspaces? All right, do you remember doing assignment questions where asked to show stuff as a subspace? Yeah. What were some of those things? Things that are subspaces. All right. Woohoo, that's one. Anyone else got one? The zero vector. Ah. You know, hashtag special case. Anything else? Yes.
Something to do with linear.
That comes in with bases. We'll get to that in a second. But where did we started this discussion with the word span, didn't we? All right. So the reason why subspaces and spans are so intricately linked is anything that is a span must be a subspace. Let's go do this. Yeah? We're loving the plan. I'm loving the plan. I'm feeling like we can do this. So again, I don't want to get too clever. All right. I can do clever things. But one of the things you're going to see about exam questions, right? They're not terribly tricky. Well, no, actually they're terribly tricky. They're not long, complicated calculations. If you're doing a 3-page calculation in the exam, you've probably missed the point. Okay. So I can go, hey, so we're going to go show span of V1, V2 is a subspace. All right. V1, V2. All right. Well, X, if we say X in span, V1, V2, exactly what I said before, is equal to C1, V1 plus C2, V2. And if C1 is equal to C2 is equal to 0, X equals 0. Therefore, 0 is in the span. I'm going to get a bit lazy at this point in time and stop writing the extra bit. Okay, love the plan. So now we're going to go let X in span. Therefore, X is equal to C1 V1 plus C2 V2. Technically, we're saying C1 and C2 are real numbers. And so we're going to go, all right, K times X is equal to, well, I can go, that's going to be K times C1 V1 plus C2 V2, which is equal to K C1 V1 plus K C2 V2. And we're going to call this D1 V1 plus D2 V2, which is in the span. Kind of a little bit anticlimactic, but that's what we'd have to say. And we go, oh, closed under multiplication by scalar. All right, writing all these words. All right. Let's try X and Y in the span. So X is equal to C1 V1 plus C2 V2, and Y is equal to, A1 V1 plus A2 V2. So X plus Y is going to be equal to C1 V1 plus C2 V2 plus A1 V1 plus A2 V2. And so I'm going to do the nice thing where I group my V2s. And so I have a C1 and an A1 by V1 plus a C2 plus A2 by V2. C1 plus A1, just a number. C2 plus A2, just a number. Because my real numbers are, the set of real numbers is actually a space. It's not even a subspace, it's a space in its own right. It's a one-dimensional space, but we're going to ignore that detail. And so these, because they're just adding 2 elements of a space, they're in the space. It's a kind of a meta thing. So I can say it's in the span. All right. Now, I've done just 2 vectors. And trust me, I'm pretty sure it's in one of the assignment or the examples that you have to do. that shows that the span of a set of vectors is a subspace. All right, so we are saying so span of V1 and V2 is a subspace. Okay, sweet. Almost too easy, right? Almost too easy. So we've got these ideas in our head, right? Now, so span, shorthand. Subspace, kind of like a space, so it kind of does nice things, all right? And while I've only got a couple of things here, there's this kind of idea here that these are, I'm going to say, they're like linear things, all right? Can we think now? There was a couple of other things you showed in one of the more recent writtens, I reckon. I reckon it was you guys. Yeah. Did you remember looking at the union of subspace?
Nicholas, can you hear us?
Robert?
The screen on the Zoom's black.
Oh, very good. Thanks, Ethan. Why are we not doing this? Okay, let's do. Did we? Come on. That one. Share. Why are we making this hard? Right, let's try that now, shall we? Okay, deep breath. We want to go 3. All right. So I'm gonna cheat a little and go. All right. Do we feel like audience participation? No, that looks really like a no. Okay, so the question was, is the union of subspaces a subspace? All right, because you all did whatever assignment that was or student question, and you go, not a subspace. All right. Union is like adding things together, not very, like kind of is, but it kind of isn't, right? Problems with that, won't go into it. Intersection of subspaces. Do we have feelings about the intersection? Do we remember doing that in an assignment question or maybe in one of the writtens or class exercises? Go on. Maths 1A hasn't changed for like 20 years. I know it's in there somewhere. All right, I'm sure just a couple of weeks ago, I was helping someone explain this to someone that actually the intersection of subspaces is a subspace. All right. This is cool and amazing. I know. All right. So this is another thing that you could be asked to show in an exam. All right. Have you ever thought about what you would do? So, like I say, I don't want to spend too long doing this, but let's consider this for just a second. So all right. So the reason now part of the reason I'm doing this, right, is through the assignments, the tutorial, the workshop questions, whatever else, we showed you some tricks. All right. There are tricks that we showed you. All right. And one of those is this little trick here for showing something as a subspace. All right. So we're going to go W is equal to U intersection V. All right. Piece of cake easy, right? So how do I know 0 is in W? U and V are subspaces. 0 is, that should look a lot more like a 0, is in U, and 0 is in V. So 0 is in W. Sweet. Okay. Let X in W. Therefore, X is in U and X is in V. All right. Great. K times X. Now, K times X is in U as U is a subspace. Okay, X is in V as V is a subspace. All right, so I can actually do these things nice and easily, yeah? And so I can go, hey, it's for it to be in the intersection, needs to be in both sets, because that's what it means. Well, hey, so Kx is in W. That gets very boring and a little bit tedious. And because you have to wait for me to not only say it, but write it, it kind of drags this process out. And so we can go through and do this. All right. There was one other thing where they had, quite literally, I'm sure you guys just did this in assignment. So one of the things you want to do is actually go through and look at those assignment tutorial questions, workshop questions, student examples, whatever, to work out what is that second thing they're teaching. It's not answering a question, it's demonstrating a technique. All right. To show something is in the intersection, I showed that it's in both of the sets. All right. And I just used the fact that it was a subspace. Didn't need to do any more. Used the fact that it was a subspace. Really easy. So you can see how that's going to go. All right. Now, we had union is not a subspace. So I said at the start, one of the things that we do is we kind of have a feel. We go yes or no. All right. So for subspaces, one of the big deals is the no. All right. So we said system of equations, which has, system of homogeneous equations. So not a subspace. Feels a little bit terrible, but if I go non-homogeneous, really should say solutions of non-homogeneous systems of equations. Doesn't contain 0. If it was a homogeneous system, it would contain 0. I would be able to go, yay, it's a subspace. Because it's non-homogeneous, not so much. So if I take a set of, X, what's the one? They love this one. X, Y, Z, such that, I don't know, X times Y times Z is greater than or equal to 0. In actual fact, from the point of view of if you look at some of the questions that were in the Mobius or in the questions that you've seen, there's something like this. And this one's really cool. All right, I hear you thinking, no, Nick, I don't think it's really cool. But this one has a wonderful property. So if I take an X, so if I go X1 times Y1 times Z1 greater than or equal to 0. All right, so that X1, Y1, Z1. Gotcha, right. So if I do K times that, X1, Y1, Z1. Yep. And so k x1, k y1, k z1. Well, if k was 2, this thing would, so this works out to be k x1. The condition I need to look at, this thing, k x1, k y1, k z1. That's going to be like k cubed. X1, Y1, Z1. If k was a positive number, this number is positive, this thing greater than or equal to 0. Sweet, yes, closed under multiplication by scalar, right? So no, so no. So one of the things when we're trying to break these things is we've got to be careful about the things we choose, because we may have picked a thing. So the clue was this says greater than or equal to 0. And so actually I kind of want to pick my scalar as negative. Yeah. Let k equal -1. Then k cubed x1 times y1 times z1 is equal to -1 cubed by x1, y1, z1, which is equal to minus x1, y1, z1 less than or equal to 0. Pooh, not in my set. Oh, I don't think. All right, not in my thing. Okay, so trap. So there was a couple of things that told me that this was not going to be a subspace. All right. Firstly, product of terms. When I multiply terms together, not a subspace. I'm going to go it's like hashtag, we can be tricky about it. All right. All right. If it has an inequality, probably not a subspace. Again, tricky thing. So to quote one of the questions that we had, so one of the, I'm not sure if it was Mobius again, because I don't do these things. 1A, that would be number 4. There was a set of x, y in R2 such that x squared plus y squared is equal to 1. And they're going, hey, check it out. I could do this. And so then they did this thing where we did the union of the points 0, 0. All right, quick graph of this thing here, unit circle and the origin. All right. It's got squared terms, so product of terms, probably not. But it does contain 0, so we met the minimum requirement. All right, can be a little bit tricky, but if I take an arbitrary element, if I take this and just times it by a number that is not 1 or -1 or 0, then it's not going to be in the set. All right, if I times by -1, I appear over here. If I times by 1, I'm here. If I times by 0, I get the origin. All right, those are 3 points where it's going to be in the set. Every other value of k gives me not, and so I can actually go, hey, this thing is not. All right. But then the very next part was xy in R2 such that x squared plus y squared is equal to 0. And who thinks that's a subspace? Yes. All right. At least a couple of you can get the idea that you can wave your hand. Great plan. Love the plan. I'm going to call that positive interaction. Right. This is a subspace because it's a trick. All right. You know how I said not generally not? All right. Special case. This is equal to the set of 0, 0. There is only one point that satisfies that equation. And that is my default subspace. And so I'm going, yeah, okay. So it's a subspace in a trivial way. Okay. Yes. So we need to do a little bit of interrogating, right? If you go, I don't think it's a subspace, I should just go, hey, can I think of an element that's in there? Can I think of an element that's not zero? So if you think it's not a subspace, what you should do is you should take an element in that space, which is not zero, and you should think about the condition and go maybe times by a scalar, maybe add two things together. Just for the purposes of for doing the for talking about how we might talk about the union of sets, what I'm going to do is I'm going to go union of sets, union of subspaces. So I'm going to take nice straight line subspaces in R2. All right. And these are basically straight lines through the origin. All right. So straight lines through the origin, subspaces. Straight lines not through the origin, not subspaces. Now, when I talk about the union, I mean everything on this line and everything on this line. All right. And so quite often what happens is people go, the point about the union is it is actually closed under multiplication by scalar. If I take this point here and multiply by a scalar, I stay on that line. I'm in the set. Woohoo. Everybody happy. But it's when I come to vector addition. And so I have to be careful about it, right? Because it's a subspace, if I take 2 points on that line, it's going to be on that line. If I take 2 points on this line, it's going to be on that line. I need to take a point from this line and a point from this line and add them up and go, ooh, not on either of those two lines. All right. So I can't just go, it's not going to be. I have to be a little bit careful about the example I used to show that it's not a subspace. All right. Woohoo. So basis. Okay. So I'm going to pause momentarily to think about all the things I should have said and go, was there anything I really should have said that I didn't? Anyone got any thoughts? No. All right. So in summary, know what it is, check to see what it looks like and see the clues, read the clues, right? Follow the clues. We are Sherlock Holmes, we can follow clues. And then make our conclusion, all right? You want to be stating the things you saw, right? I saw this, therefore this, all right? Now, the reason basis fits right next to this is because every subspace has a basis. All right, every subspace has a basis. Great, everybody's excited by this. Now, when we're talking about a basis, damn, what is a basis? All right. I've kind of put in 0. All right, notice how I've kind of like, I believe things come in 3. But really, bases are kind of like, there's really 2 things that you need to remember because there are a set of vectors in the space kind of doesn't need to be said. It's kind of implied by the fact that by the space being equal to the span of those vectors and the set of vectors all right, running linearly independent is just a pain in the ass. Way too many letters in that word, those words. All right, so it is actually a wonderful thing, all right? So you're going, hang on, but Nick, why would you do this? So there was a wonderful question in one of the exams a while back. Don't know how long ago because they don't let me see the exam anymore. But there was 4 things. There were 4 things, and go, here's a space, And here's a potential basis. Which of these is a basis for this space? Okay, so ways a set of vectors cannot be a basis for the set of space. All right, anyone got thoughts? What? We. All right, that's a great one. That's usually the right one. Okay, what's another way? Sorry? If their vectors don't span. All right, you're seeing, I'm glad you picked up on that one. Now, so the reason 0 is in there is kind of like a bit of a dodge, right? All right. All right, it's this one where they say the vectors are not actually in the space. All right, you would think that we'd know better than to give you a vector that's not in the space as a potential element of a basis, but no, you should check. All right. So I love this question because like there was 4 of them, and none of them were a basis. I thought it was great. I'm like, sweet, how to subvert expectations. All right, a lot of students who had all the working right go, but no, one of them's got to be, and so they picked one because one's got to be a basis. No, it don't. All right. So linear independence. How do we show linear independence? All right, so if I want to show linear independence, I show that my linear combination of vectors equal to 0 has only one solution. All right, we all knew that. Everybody excited by that. Now, and so it's really important that we know what we're doing, all right? So we're going to form A from the vectors as column, solve AX equals 0. So if I get a unique solution, my system has, and my vectors are linearly independent. All right, so it's really important. We do not say a matrix is linearly independent. All right, linear independence is a term that applies to a set of vectors. We can construct a matrix from a set of vectors, but a matrix is not something that is linearly independent. The set of vectors that form this matrix as columns can be linearly independent. All right. It's really important to remember that. And we said, hey, if I do the row reduction, if I put it in reduced row echelon form, pivot in every column, vectors are linearly independent. I'm done. All right. Woohoo. But that's the same as saying there is a unique solution. All right. So homogeneous systems, remember, only ever have one solution. All right. So, right, that was like that was like the first one of these things. So how am I going to go about showing some vectors span? Any thoughts? The thoughts there, I spent too long talking and not enough time writing? I don't know. So now, the reason we don't have thoughts about this is because it's actually kind of hard. All right, this is actually one of the hardest things to do. So what we're going to do is that's going to be my first step. All right. All right, the next one is a bit dodgy. All right, because the thing I'm going to do is I'm going to go, have I got enough? All right, have I got enough vectors? Okay, now, like I say, this is one of those things where how many vectors do I need in a basis? Sort of. I'm going to translate that slightly to say I need the number of vectors that is equal to the dimension of the space. All right, because remember, I might have a subspace in Rn, but it might be dimension k. All right, so I need k vectors. If my space is dimension k, I need k vectors. But it's kind of a bit weird, but if I need k vectors, how do I know what k is if I don't have a basis? All right, so this is where showing span is actually kind of hard. All right, it's sort of really difficult to show that you have enough vectors. All right, and so one of the things we do is we kind of gloss over that detail. All right, so we check that all the vectors are in there and that there is enough, and we use a little bit of sort of logic for the dimension. All right, if I have things in R5 and I've got, say, 3 things, but I've got these things in R5, potentially dimension 5. If it was dimension 5, I'd need 5 of them. If I have 2 equations that restrict that, I'd bring it down to 3. And so I'd need 3 vectors in there, right? So it can be very difficult to decide if you have enough vectors. None of the questions you get in the exam will be that hard. They will be, so if I tell you something like we had sort of X, Y, Z in R3, such that X minus Y is equal to 0, very much like an exam question, you would go, hey, 3 dimensions, 1 constraint, that means I've got to have 2 vectors to span it. All right, so I can sort of know by looking at it, right? And so there is actually, we don't tend to ask explicitly to show that these vectors span. So when we think about how we create some of these things, quite often when it says give a basis for, all right, give us basis for the null space. Oh, you guys haven't talked about null space. Sure. Have you heard the term null space? Sweet, that's what I thought. So give a basis, so give a basis for x such that ax equals 0. It's a homogeneous system of equations. I know it's a subspace, therefore I know it has a basis. Now, this is one of those funny things. A lot of what we do is what we would call a construction of a basis. Okay? So when you go through and do your row reductions, you go, these are my basic variables, these are my free variables. Free variables get parameters. I can actually write it out. So you know how we do this thing where we go, all right, x4 is equal to s and x5 is equal to t. And so therefore x1 is equal to x2 is equal to so on and so forth. What I can do is I can write that out as s by some vector. I'm going to call it v1 and t by, call it v2. That is just a fancy way of saying span v1, v2. All right. So the construction process gives you a basis. All right. So it's important to recognize that some of the things you are doing, some of the things we've been teaching you to do since high school are actually things to give you a basis for the thing. So it's actually sort of inherently answering questions. All right. How do we feel about that? Sure. We're going to turn the mic off for a second. Right. Sweet. Okay. I think we've done it. So we're all feeling better about span, basis, subspace? Hopefully. I think what we might do is we might go, the next thing on my list said unbounded feasible regions. Okay, so we're talking convexity, and interestingly enough, on the list is convexity. So some of this is what might we ask you to do? So convexity. We should do 1A and we should look at the last page because we're starting to get more. We're up to page 6. Slick. A set W is called convex if all right, beautiful. So that's what it means to be a convex set. All right. And we also said, there was also a thing that said there was a theorem, and I may get it exactly a little bit wrong, that if f is a linear function, so if we have some linear function on a closed bounded set W, closed bounded and convex set, all right, then f so we say something like f achieves max and min on W at the vertices of W. Now, definitions, and part of me is going, oh, is that exactly what it says? And I'm going to ignore whether I've got that completely right. You're going to check in your notes, all right? Because I make mistakes. Unfortunate. Trust me, it's terribly unfortunate. But that's the idea. So how do I show if something's convex? All right. What I'm going to do, consider. Now, again, I know this was in your assignment. X in, I'm going to say R2, such that X dot the vector, I don't know, 2 minus 3. Greater than or equal to 7. 7 is always a good number. All right. Do we even know what that looks like? Sweet. Do we need to know? This is one of those out there ideas. Do I need to know? No, I don't. I don't. Now, what's my plan? I'm going to call this set W because all my sets so far have been W and we really love them W. Sure. My thing said if I take 2 points in my set, then the line joining them has got to be in the set. I'm going to start with 2 points in the set. Let's, oops, how about I write let U and V in W. So what that means is therefore U dot with 2 minus 3 greater than or equal to 7 and V dot with 2 minus 3 greater than or equal to 7. Loving it. All right, now you have done this either in lectures or in class. All right, I am going to take X, which is equal to T times U plus 1 minus T times V. All right. Now, I'm going to go 0 less than or equal to T less than or equal to 1. Okay, so some of those looks that say, I've seen that before. What the heck? Hey, I know where you're going with this. And some of those looks are really saying, no, I've not seen that before. So let's pause momentarily and consider what on earth I just did. All right. This is a way of describing a point that is on the line segment between U and V. Okay. So this is our trick. Our thing says that the points on the line joining U and V, so the line segment between U and V must be in the set. So if I take 2 points in the set, got to be inside the set. Love the plan, right? Who doesn't love the plan? But this is this is a trick we want you to remember. All right, that this form gives you a point on the line joining those two things. Quite literally, after the appropriate first year maths exam, had massive argument with one of my friends about whether this was the right thing to do. Hashtag, I was right. I like these stories because I was right. I don't tell you the stories where I was wrong. No. So what am I going to do? Well, the condition is the dot product with this. So I'm literally going to do T times U plus 1 minus T times V dot with X. Dot with 2 and minus 3. Now, properties of dot products. I know you're thinking, but what, Nick? This should be equal to T times U dot with 2 and minus 3 plus 1 minus T times V dot with 2 and minus 3. Okay. Now, but I said U dot 2 minus 3 is greater than or equal to 7. So if I replace that number by 7, that by 7, and that by 7, so this is going to be less than or equal to, did I do that the right way around? Let's pretend. No, wrong way around. Wrong way around. Less than or equal to, oh no, that bit. Less than or equal to, no. Yes, this bit. This is going to be T by, I'm going to say 7. and plus 1 minus t by 7. That by greater than 7, that by greater than 7. That's got to be greater than. Did I do that the right way around? No, that number is bigger, so I've got that the wrong way around. That should have been that way. Beautiful. That makes more sense. Because I've replaced this by the thing that is smaller than it, and this by the thing that is smaller than it. This is what I mean by your brain switches off when you're in lecturing. Kind of. But this is just 7t plus 7 minus 7t is equal to 7. So I've got my x dot with 2 minus 3. Okay. Thank you. That's going to be greater than or equal to 7. That's what I want. Beautiful. Oh, hey, hang on. X is in my set W. Now, I didn't even say what U and V are. I just said they're in the set. So there are any points in the set. And hence true for every point in the set. So this is that joy of going, hey, because I didn't specify what it is, it must be true for all. And so therefore I can go, W is convex. Okay, so that's, now, it is not impossible that you will get asked to show that a set is convex, okay? Or justify that a set is convex. So, do we think, so we've got set operations, right? We know about set operations, union, intersection, sort of stuff. Do we reckon the union of two convex sets is going to be a convex set? No. Well done. All right, those of you paying at home, paying attention to this one. It was so. I can construct any number of cases where it is true, but in general, I can't assume it's true. All right. Intersection. Anyone got a feeling, yes or no? All right. Now, I do remember a year when they put in, here's two convex sets, shows that the intersection of these two sets is convex. That was done universally very badly by students, right? When really it's a nice simple, if X and Y is in this set, then the line joining them must be in the set. And if X and Y are in this set, the line joining them must be in this set. So the line joining them is in the intersection, not terribly hard. But learning that trick, all right, which we talked about for subspaces, is actually one of those things. And it goes, so applied for subspaces applies for convex sets. All right, so transferable skills, people. All right, but it is still a difficult thing for you to see straight up. And part of the reason why I'm telling you, I do not think that they will ask you to show something like the intersection of two convex sets is convex. However, all right, when you think about what you're doing, so I'm going to take my little condition here. So I had x, let's say xy dot with 2 minus 3 greater than or equal to 7. That's going to tell me that 2x minus 3y greater than or equal to 7. So that's that same inequality. All right, same inequality, everybody happy. One side of it, it's going to be a line that is loosely, I don't know, y should be negative, x should be positive, yeah, sure. Something like that. And we are one side of the line. We are probably that side of the line. Maybe, no, that side of the line, isn't it? Sure, that side. All right. So this is a way of getting a nice straight line equation. Yeah. And so when we think about how we define these sets for that linear optimization, all right, linear optimization, oh my gosh. Okay, well, when you think about what you're told, let's do your standard optimization problem, all right? So, so f is equal to, I don't know, x plus 4y given, let's see, what is that? That would be like a x plus y less than or equal to 7 and 2x plus 5y less than or equal to 3. Yeah, sure, whatever. Hang on. X, y greater or equal to 0. When we think about what's happening, this is implicitly asking for the union of this set and this set, and the set where x is greater than or equal to 0 and y is greater than or equal to 0. We're actually using the fact that the intersection of convex sets is also a convex set, all right? We're using that to say that this set is convex, all right? And I think it's really important, and I'm going to be honest, right? If half of you actually start 1B with this, we're remembering this idea, it will be a big win, all right? Because this is one of those things we're building on, all right? It's not actually a thing we need to know specifically for anything there, but that idea that these things carry over, that we've shown these things in this way. And so, great, we've got intersection of sets. All right, now, when I went back, I'm going to go back just a little bit here and talk about, I said closed, bounded. Closed for what you're, does anyone remember off the top of their head what closed means? So those of you who go on to do a thing called real analysis will get a way more technical definition of closed. All right. And there is lots of fun things to do with closed and open and stuff. But, you know, hey, for where you are, closed, bounded. All right. A way to put this, and this is a very informal way of saying it, but I can put a line around it. Another way, like actually one of my lecturers in first year said, if you can put your hand over it and cover the whole thing, then it's bounded. And if you, and someone goes, but what happens if it's a bit too big for your hand? And he's like, zoom out a little bit. So if you can zoom out enough so that you can cover it with your whole hand, then it's bounded. All right. There's a whole lot of technical definition and stuff. And again, depending on what you're trying to do, how definition is. Now, there is a horrible thing. So when it comes to linear optimization, there is two major problems. All right. And one of those is about where these equations come from. All right. And I'm not going to address that right now. Okay. So it's really important to go, possibly pause for a second there. One of the things that if you look at the Mobius questions that talked about doing this process of finding this, stating the linear program to solve, about stating the objective function, the thing to be optimized, stating the constraints, was those questions all started with defining very carefully what you could control. okay? And that is the thing that tells you what to do. Going to be honest, like when I started doing optimization problems, what I did is I said, that number can change. I will call that number X. I will call that number Y. One time I got to like 16 constraints and I'm like, I feel like I'm getting carried away here. But then when I started looking at the things that were restricted, the things that had bounds on them, that made it a lot clearer which things, all right? I could write it in terms of this, or in terms of this, or in terms of this. There was one natural way to do that, right? So there is, I'm not going to suggest it is the best strategy out, all right? But if you're not sure what to do, make nice, clear statements. X refers to this quantity, and make it a quantity. Number of bags of this, number of whatever, right? Number of kilograms of whatever. By making those nice, clear statements, you can go, this thing is. So, and you will be told that you have to have this much of something or other, and it's got to be at least this much or no more than this much, right? And those things will help you determine it, right? So for everything that is limited in some way, you get a constraint. And so you can literally go, hey, there were 3 limits mentioned in the question. I should have 3 constraints. Oh, there are these things involved in this. And there is nothing wrong with giving names to something that you do not end up using, all right? Better to say, this is what I'm calling it, and never use that thing, than to not give it a name and then not, and have to use it in there, all right? Because if I'm marking your thing and you go, hey, the constraints are X plus Y is less than 7, I'm going to go, sweet, that's awesome. But you didn't tell me what X and Y are, and so you're going to lose a mark, okay? You need to have said, if your thing involves X, Y's, and Z's, you need to have said X is this, Y is this, Z is this, okay? Now, we said bounded. One of the things people wanted me to talk about was what happens when it's unbounded. What can I say? All right. So one of your problems in the Mobius actually talked about a situation where your constraints, I'm going to just sort of sketch it out. I could have that side of that line and that side of that line. So my feasible region, there was a reason I brought textures, was all of this region here. Now, kind of goes up forever, kind of goes across forever. That's a bit of a problem. It's a problem. What am I going to do? Well, this doesn't mean I can't solve this problem, all right? So now, from a geometric point of view, what can happen is my F, I can have a line, say, this will be F of my X, Y is equal to some number, all right? Some number. And so what happens is if I move this line in one direction or the other, usually in a direction that's perpendicular to the line itself, is the way I am going to get something like F of X, Y is equal to a larger number. All right. And so I can actually go so we can find a minimum. All right. Now, so without talking to whoever put in the thing, put in the suggestion, when we're talking about that optimization idea where we're going, we can find a minimum, we know that what we're going to do is we're going to list the vertices, all right? So if I go back up to my constraints, so I had my X plus Y less than or equal to 7, we're adding slack variables, all right? And so we'd have like an X plus Y less than 7, so I'm going to add S1 is equal to 7. And so that is just a gap between S. And so in actual fact, what you're doing is you're pushing that up into a higher dimension. You're rather than doing x plus y is less than or equal to, you're pushing it into a higher dimension, and so you're getting a line segment. Or you're getting technically to be a plane segment, if you like. And so when we do the 2x plus 5y less than or equal to 3, they need different slack variables. They're obviously going to be two different values that do this. But this same process for creating these will create the equations, all right? So we've seen when we add in, I'm going to put it, that's a good idea. So I could add in x minus 2y is greater than or equal to 4. And so that's when we have to do that extra step, all right? Where we have to go, oh, okay. First thing I'm actually going to do is multiply through by -1. So minus x plus 2y less than or equal to -4. Now, I'm hearing you say, did I have to do it that way? And the answer is actually no, right? You didn't have to do it that way. But with a lot of things we do in 1A, we do it specifically because we want you to get used to doing it this way, as opposed to, so I'm like, when I add the slack variable, so minus x plus 2y plus s3 is equal to -4. I could have gone here and just gone, oh, x minus 2y minus s3 is equal to 4. I could have done that, all right? And that equation and that equation are equivalent, all right? I don't want to do this, all right? I don't want to get into the habit of doing this, all right? Because when I come to do further things with these things, all right, we want to get used to doing it in this way. We want a nice systematic way of doing it, all right? Because now, linear optimization, a lot of your life has been improved by linear optimization without you knowing it, okay? This was, admittedly, we're talking, this was big in the 60s and 70s. Most of the advancements in it have been done, but even like one of the people I know did a whole master's thesis on using techniques around linear optimization, around literally this sort of idea, to actually work on sort of wastewater management in South Australia. Stuff, not going to go into it. But anyway, basically an extension of these ideas, all right? This is maths that is actually used to solve problems today, effectively. It's still used because it's a really powerful technique. A lot of systems that we construct fit these models, all right? So we still go through the process. So let's, like, I'm going to just go through and go, well, if I'm doing this, I'm going to put these into equations, all right? So I'm going to have like an x, a y, a S1, S2, S3. And so my thing is going to be 1, 1, 1, 0, 0. And then we're going to have a 7. And then we're going to have a 2, a 5, a 0, a 1, a 0, and a 3. And then we're going to have -1, a 2, a 0, 0, 1, -4. Okay, so same process. I have 3 rows, so therefore I need 3 pivots. I can talk about basic solutions. All right, so basic solution is where I've identified 3 variables as the numbers I'm going to read off, and 2 variables I'm going to identify as 0. All right, so this one makes it nice and easy if I make those first 2 equal to 0. If I make the first of them 0, I can forget about them, and then I can read off the solution. And so I can then go 7, 3, -4. And because we've put in my slack variables to be positive values, I can go, there's a negative number there, it's not feasible. It's not a vertex in the feasible region. Strictly speaking, it will correspond to a vertex somewhere, but not in the feasible region. And because this corresponds to the point 0, 0, so the origin. And so that quite often corresponds to the constraint where x is greater than 0 and y is greater than 0, where those two meet the origin. This is not going to be an unbounded region, but I'm going to worry about that later. So I can do this. Now, there's a couple of things that, so if you asked me about doing this in the Maths Learning Center, I would have said, well, I've got 3 out of 5 variables that have got to be pivots, all right? And so what I would do is I would actually write down 3. I would go, well, it could be 1, 2, 3, or 1, 2, 4, 1, 2, 5. That's it. 1, 3, 4, 1, 3, 5, 1, 4, 5. Those are all the ones where 1 is a problem, where 1 is one of the pivots. And so I have to go to 2. And so 3, 4. These all have to be different numbers. So that's how I'm making this decision. And so my system, I've worked out this one there. So now I'm going to assume that the lecturer did this for you at the time. But this is still going to get what's going on here. All right, so I'm going to be able to determine, quite often we'll go feasible as a, and we'll go, not feasible. I don't need to think about it anymore. You can actually add the vertex that it is afterwards. And then sometimes we can put in objective, what the value of the thing I'm trying to optimize is. And so from this, I can just read it off. So setting it out as a table where I've got all of these listed, this can help you to see if there's any of the possible ones you have mentioned are missed. Now, let's come to the raw prawn. They're not going to ask you to solve it in the exam. So what are they going to ask you to do? So if we go back to how we were originally setting it up, all right, we can think about this in sort of in a group of components. All right, so when I'm stating, so an exam question that they love, state the linear optimization, state this problem as a linear optimization problem. All right, and you need to do all right, so 1, state objective. So the F and max or min need to be quite clear. This is the objective. This is what I'm doing. All right. So I need to state the variables. X is number of kilograms of this. Y is number of kilograms of that. Z is the number of people. I don't know. State the constraints. So if you look at it, I've said what F is, maximum, minimum. Stated my variables, made a clear statement about what X is, what Y is, whatever, all the variables. State the constraints. Now, going to sound like a silly thing. Say that. All right. You actually have to say that X and Y have got to be greater than or equal to 0 for the problem to be correct. All right. And like back when, it's been a long time since I've marked first year exam, and I mean a long time, but back when I was marking it, this was something that you had to state to get full marks. All right. So quite often I will state this as state the objective function and state whether you're creating a maximum or minimum. So if you think about it as 4 or 5 things that you've got to state the problem. Watch out for the words. All right. If they ask you to state the problem, they are almost certainly going to say, do not solve. All right. This is really, really important. All right. You can waste a lot of time trying to solve this problem. You can come up with an answer. If we haven't asked you to solve it, we're not giving you marks for it. It's really tragic. I always feel really bad when that happens. But then I move on because I've given you 0. All right. So you've got to make sure you answer the question that's been asked. One of the doctors I know, he used to write on his hand, so he'd actually have it on his left hand, because he'd have his hand like we'd be writing and he'd have it, and he put RTBQ. All right. And RTBQ, read the bloody question. Actually give me the answer to the question. All right. Read your, like, not many of you are going to have done lots of essays in your time, because math students tend not to have done a lot of math and a lot of English. Some of them you have. I definitely didn't. But in an English essay, you wouldn't dream about handing up an essay without having read it, would you? In a math exam, you read your answer. Did I answer the question that was asked? Is the thing I've written on the page an answer to the question that was asked? Or is it working that will allow me to answer that question? And I need to state that final line. Because quite often when I'm marking the exam, that final line, the thing I'm looking for, that is the thing I'm going to give you marks for, is stating the answer. And you really, really have to remember that we've asked you a question. It is finished when you've stated the answer. All right. And this is a really good thing. This is like state the linear program, say all of these things. All right. Very often followed in bold letters, do not solve. We don't want the solution. We just want you to tell me what the problem is. All right. The other part. So this is, you know, this is fairly likely on the possible questions, right? Next on the list of possible questions is all right. So next, possibly, tell me what the linear program is. First and most popular question among lecturers, let me tell you. Number of those questions I wrote were actually, really, it's only about 5 or 10, to be quite honest, because after you've written 1 or 2, you go, oh, this is really boring. I don't want to have to do this. But there is, I want to state more. I want you to give the formulation of the problem. The next step is put it into matrix form. All right. State initial basic solution. All right. All right. So if we are going to go add select variables, put it into matrix form, we're going to follow it with state the initial basic solution. All right, like I did with the thing there, that's that one. We are then going to, so quite often that is followed by, not always, but often followed by do this particular row operation or do a row operation and state another basic solution. I've seen one of the questions that I thought was kind of fun was give a feasible solution and give a feasible basic solution. All right. So they wanted you to do, if you knew what you were doing, you didn't actually have to do any row operations. You could just read off another feasible solution for that problem. All right. There was a feasible solution and there was a not feasible solution that you could just read off. It was great. But we do not want you to do a lot of calculations. Like you look at the one I did, right? I've got like 3 by 6. I don't want you to do many row operations. If I want you to do one row operation on that, that's all. I'm not into making you suffer. But I do want you to demonstrate and how if the system changes, how to read off the basic solution. All right. So thinking about it from that point of view. All right. So I think I'm running out of time. Now, so hashtag, I can go on until about 6 o'clock where security will come and go, what are you still doing here? Nobody wants that. I am going to spend, to talk about upper and lower sums and doing integration by trig substitution is going to take a little bit of time. I would like to do the upper and lower sum thing as a minimum, because I think that is a thing worthy of talking about for exams. It is a thing we are likely to do in the exams. In fact, it's almost a given in the exam, okay? We are going to get you to do something that involves upper and lower sums. So, okay, let's pick on an integral. Now, I'm going to go, I don't know, what's a good one? Maybe we'll do something a little bit different. We're going to go integral from 3 to 6 of x squared plus 2x dx. Okay. Sure, I've got that right. Okay, so the question is going to say something like find UN and LN. All right. That's what I'm going to do. I'm going to pause here and see that one. And I want, where did it go? Ah, poo. We might come back to that. Questions on the thing might come back to them, might not. I will keep going until I've done this stuff and check the questions. But at about 10 past 4, I'm going to give you an opportunity to walk out of here politely. Because I do think me talking for more than 2 hours, going to refer to my the comment at the start. I do like the sound of my own voice. I will keep talking. So I will keep talking just to tick off the boxes. This will be recorded. You can watch it back at double speed if you want. So when we're doing this, right, in programming, quite often there's a lot of stuff that we put at the start of a program that we kind of have to put in just to say, we're about to write a program. The program's going to need to use these things. I'm going to use these as variables or whatever, right? This is known as preamble. Preamble for an upper and lower sum is A is equal to 3, B is equal to 6. My interval width, which I'm going to refer to as delta x, is B minus A on n. In this case, 6 minus 3 on n, which we will just write as 3 on n. xi is always equal to A plus I times delta x. In this specific case, that means 3 plus 3i on n. I am going to observe that this function is increasing on this interval. All right. That means my maximums are equal to f of xi, and my minimums are equal to f of xi minus 1. All right, because my ith interval is xi minus 1 to xi. My maximums are going to be equal to 3 plus 3i on n squared plus 2 by 3 plus 3i on n. I humbly recommend you do the algebra to simplify, expand and simplify this expression before you put it into the upper and lower sum. All right. So in this case, it's going to be 9 plus 18i on n plus 9i squared on n squared plus 6 plus 6i on n. A little bit of simplification. So I'm going to have 15 plus 24i on n plus 9i squared on n squared. All right. Upper sum on n intervals is equal to the sum from I is equal to 1 to n of delta x times my maximums. Delta x sits out the front of my sum. And so it's going to be 3 on n times by sum. And then 15 plus 24i on n plus 9i squared on n squared. All right. 3, I should put brackets around that, on n. And so we're going to break it into sums. Summation 15 plus summation 12i at 24i on n plus summation 9i squared on n squared. Ideally, I should say I is equal to 1 to n for all of these, but that's just getting tedious. 3 on n. All right, this is going to be 15n. What I'm going to do here is we're going to go 24 on n, summation of I is equal to 1 to n, plus 9 on n squared, summation I squared, I is equal to 1 to n. Okay, now, I am not going to finish this problem, okay? Firstly, it's tedious. Secondly, you guys probably want to go home, and it's going to take another 5 or so minutes to work it out. But what we can do is we do expect you to know that the sum of like 15 is just going to be 15n, that sum of I is going to be equal to n plus 1 on 2. Now, we kind of do expect you to know I squared is equal to n plus 1 to n plus 1 on 6. Hashtag, we kind of expect you to know, but usually if it's expected to be done in an exam, we will tell you that, all right? So don't rely on it, because we kind of expect you to know, but also the first two we won't tell you. That last one, I squared, sometimes we'll even use I cubed. But we will tell you what it is, all right? And I don't even remember what I to the 4 is, so I'm pretty sure we don't ever do that. So this is now just a matter of expanding and simplifying. Because this is a squared thing, all right, I should end up with some number plus number on n plus number on n squared. I'm not going to do it because it's tedious, all right? With upper and lower sums, all right, because of this property where this is this, all right, I can actually do a dodgy trick. Dodgy. I should write a page number on here and go 1A. My lower sum, which is going to be summation of delta x f of x I minus 1, I is equal to 1 to n. Dodgy trick. So delta x always comes out the front. I is equal to 0 to n minus 1 f of xi. All right. So my function now, this is great. All right. If the number of intervals is n, this is what you got to do. Okay. Now, what happens if I say L4? I want you to calculate the thing on 4 intervals. What changes? Don't have to use n. But more importantly, I know all of these numbers. I can actually work them out. Okay? So there's a bit of a rule of thumb with summations. All right? The rule says if it's more than about 6, there's probably a way of making it simpler. If it's less than about 12 numbers to add up, you might be better off writing them out and adding them up. All right. So the plan, the trick, the thing to watch for. If number of this is approximately 6. All right, approximately 6. All right, I've seen 6 in exam once. Usually it's 4 or 5. Sometimes it's been 3. Depends on how bad we're feeling. So I'm doing an upper and lower sum. What could be my trap? Click. Well done. Thank you very much. Trap. All right. So this is always a thing. Okay. We always do this thing where we go, oh, check this. It's only really nice and easy thing. And then you go, actually, the maximum or the minimum occurs within inside the interval. So let's pretend we have a nice quadratic. All right, and then we have our intervals. But this point here is the minimum. All right. So I can see the maximum nice and clearly from here, but the minimum is from the actual minimum of the quadratic. So if it's quadratic and the turning point is within the interval, quadratic, cubic, they won't do anything worse than the cubic to you. Trig functions, they love trig functions. All right. So if you are expected to do the upper and lower sum of a trig function, that is also a thing. The worst thing I've seen them do to you in exam, all right, was do the upper and lower sum for that function and for that particular interval. All right. And speaking as the person who had to mark it, what I was told to look for was that. If I'm getting you to do an upper and lower sum, all right, you can exploit geometry. Cosine is a symmetric function around the y-axis. I can go from integral from minus pi on 2 to pi on 2 and go, hey, but it's symmetric. So the bit on this side is the same as the bit on this side. So I'm just going to do 2 of this side. All right. You are allowed to do that by making the observation that cosine is symmetric around the y-axis. Okay, so this is the point where I pause and go, hey, maybe you guys want to go, oh, I've had enough of this. 2 hours of sitting on my bum listening to Nick talk is just like 2 hours too many. Or we can talk a little bit more about doing trig substitutions and the flags to look for. Remember, this is being recorded. It will go up online in the next day or two through our website. So if you go to the university website, so you have something wonderful like www.adelaide.edu.au. You should all be used to that by now. That is the Maths Learning Centre website. And if you then go resources, there's a thing that says resources. I click on that. Not even I do that. Then there'll be a thing where you can scroll down to Maths 1A. All right. We say Maths 1A, not 1A. So it's not at the top, it's down by M. All right. So feel free to take a moment out. I'll give people 5 minutes to sort of pack up and leave. And also I can then look up immediate trig substitution to do from my book. Because at some point in time, making up questions on the spot is hard work. All right. Thank you all for your attention and for turning up. It's been great. It's probably one of the biggest turnout I've had for a revision seminar. So makes my life a lot more fun. Yours. Yep.
Like, can you reopen the previous modules?
So all of the previous Mobiuses you should be able to review. I forget exactly how that's done because I don't play with it anymore. But you should be able to go back to any of the Mobiuses that have been finished for more than a few days. So I'm not sure when the last one closed, but so the last one might not be available, but the previous one should be available.
Oh, so it should be like the day after.
Yep.
Yeah.
You should. Usually it's about a week for Mobius.
Oh.
All right, so they'll give it about a week. The lecturer, so the coordinator, if it's like it was, like, so you've got to remember, I haven't actually done lectures for the School of Maths for 15 years now. But you had to go in and click on a thing to say publish it. So publish, or it's like publish for review or something or other. So, but there is an option to go in and go, hey, go back and review this. No worries. All right. So I saw possibly one of the most horrible things here. So let's try and write it down. Okay. Now, so when you do trig substitution, have you guys ever grabbed one of these textbooks? This is Stewart's Calculus. It's our class. But if I look on the table of integrals, if you look, where did I do? It's here. So some of these ones, nope, not there. This one, involving this, all right? So see how it's got involving this square root of a squared minus u squared. All right, and we will notice horrible thing has a inverse sine function. So horrible thing, inverse sine, horrible thing, inverse sine. And then we go around to this form. Notice it's the other way around from this. Ugh, even worse. We come down to here. So these ones, different thing altogether. So when it's sort of u squared, so variable squared minus constant squared. as opposed to constant squared minus variable squared. So these are one form. These are usually a sine or a cos substitution. I'm going to write this down in a second, but where's the one I'm looking for? Where'd it go? This one, plus. All right. So should we? No. I want. There is one. There is one. Some of the ones that look like with the plus can involve easier done with a tan substitution. These ones suck, all of them. Anyway, okay, so this one here, I picked on this one. Now, part of this is recognizing the thing that you're going to do to make your life easier. All right. And I see that look on some of your faces like, I'm going to do what now? So I'm going to rewrite this 4x squared plus 9. And I want to make that 4 by I want to make it look like that. All right. I know. Nobody likes that. So I've kind of got to get a bit creative with this. All right. So what I'm actually going to do is I'm going to go 4 by x squared plus 9 on 4. Now, still not making me very happy. All right, I'm trying to think. So what I've got to do is I've got to try and go, what I really want to do is write this as like, what's the thing? So I want my x squared to work out to be something like 9 on 4 tan squared theta. And so I want my x to be 3 on 2 tan theta. All right. Not a huge fan, but it'll work. Aha, that's what I've got to do. Yeah, sure. So I'm going to be blunt. I usually go, it's got to look something like that, right? And so because I don't go, it's definitely this thing, right? I don't have it's definitely got to be this thing in my head because I don't remember them. I play around with it just like I've done here. I'm like, oh, I know this is the thing. This is the identity that I want to use to simplify this thing. And so that's why I'm going to use that. I'm going to play around with it to make this work. So let's just check, all right? So we know x squared is going to look like this. And so when I do this, I'm going to be able to pull the 9 on 4 out the front. All right. I want that to really say equals. And so if this is the case, dx d theta is going to be equal to 3 on 2 x squared theta. Sweet. That doesn't look like a lot of fun either. So this is what happens when you put your finger in the book at about the right page and you go, hey, that looks like it could be terrible. All right. This is kind of like a worst case scenario sort of job, right? So I'm going, oh, okay. So I've recognized that I've got an x squared plus a constant squared, an a squared type of thing. And I've gone, it's going to work out. I'm just going to keep playing around with it. Oh, do you want to pass that to me? Everything locked up? Sweet. Thanks, guys. See ya. Sweet. Evidence you're been spending too long talking. Staff are walking off. So differentiate, and then I reorganize. So I'm just going to go, that's going to say dx is equal to 3 on 2 sec squared theta d theta. All right. And I'm going to go 4x squared plus 9 is going to be equal to 4 times 9 on 4 tan squared theta plus 9. That's going to cancel. And so I'm going to end up with, that's going to be 9 by tan squared theta plus 1. See what I did wrong? Need to, right, sure. Gotcha. Which I'm going to simplify as 9 sec squared theta. Slick? Everybody happy with that? Put stuff in. So we said x was this, so I'm going to go 3 on 2 tan theta cubed. 3 on 2 sec squared theta d theta. On 9 sec squared theta 3 on 2. Well, that's horrible at the best of times. So I've got a 3 on 2 to the power 3 times 3 on 2. Going to put those out the front. Tan cubed theta times sec squared theta. Loving it. Who's not loving that already? And then I'm going to have 9 to the 3 on 2, and I'm going to have my sec squared to the 3 on 2 is going to be sec cubed theta. All right. Stuff has got to simplify, peoples. All these numbers can come out the front. So I had 3 to the power 4 on 2 to the power 4 times 3 to the power 3. 9, this is going to get me that. I am going to have a tan cubed theta. Whoops, yep, sure, thank you. Tan cubed theta. This I'm going to cancel with most of this. Okay. Now, I'm going to cancel that down a little bit too. I don't know. Thinking about this, I am going to, so this thing sucks. All right. I'm going to go 3 on 2 to the power 4. Integral tan cubed is going to be sine cubed theta on cosine cubed theta. Dividing by sec, I'm going to times by cosine, cos squared theta, cos theta, cos theta, d theta. Way, that one I can cancel with one of those. So I should end up with 3 on 16 integral sine cubed theta on cos squared theta d theta. Now, I don't really want to have to do this, but I kind of do. Yes.
What if we expand that in the denominator?
I could do something like that. This is one of those things where actually, because I've just picked, like quite literally just gone, hey, let's try and do that. I don't actually know what, I didn't bother looking at where the answer went. I'm like, you know, I'm going to do it. Can go terribly wrong. All right. When you pick questions out of the book on the fly, doesn't always. There is a thing that I do notice about this, so I like what you're saying, but also I'm going to do a trick. All right, so I'm going to write this as 3 on 16 and then integral. And so sine squared, I could write as 1 minus cos squared. So I can go sine theta 1 minus cos squared theta d theta cos squared theta. Now, I think what I'll do is I will write it this way. So there's a couple of things I could have done here. So I can write this as integral of sine theta on cos squared theta, d theta, minus integral. I've got cos squared and cos squared, so I can write this as sine theta d theta. Give me 2 seconds. Oh. Okay, beautiful. I'm going to do it that way. Whoops. All right. Going to do it that way because this one, so if I'm going to do integral of sine theta on cos squared theta d theta, let u is equal to cos theta, du is equal to minus sine theta d theta. My integral becomes minus du on u squared, which is going to be equal to 1 on u, which is equal to 1 on cos theta, which is equal to sec theta. All right, beautiful. And so, and this one, so that one becomes that one becomes, this one is just going to be equal to minus integral of sine. Integral of sine is cosine, so it should be minus cosine theta, minus cosine theta d theta. And so I should end up with, where did I go? My integral from x cubed on 4x squared plus 9, 3 on 2 dx has become 3 on 16 sec theta plus cos theta. Technically, we're going to go plus c because it's an indefinite integral. And I'm going to write page 13 on there. All right, so did that. Now, if we go back up, x was equal to 3 on 2 tan theta. And so, if I draw myself a nice little triangle and go, hey, this is going to be theta. If I call this number 3, no, opposite. Yeah, no, that's right. Opposite over adjacent. 2x. This thing here becomes 4x squared plus 9. And so I can go cos theta should be equal to 3 on square root of 4x squared plus 9. And sec theta should be equal to the reciprocal of that, square root of 4x squared plus 9 on 3. Woohoo! Okay, and so I can then take this and go 3 on 16. This little trick with the triangle, when you get complicated questions like that, that can be a really useful way to sort of get back to things in terms of x. All right. And you've seen what I've done is I've got tan theta and I've just gone, tan theta is opposite over adjacent. I'm just going to make the numerator the opposite, the adjacent. And if it's just a single value, I make this side 1. So I make the thing I'm dividing by 1. Okay. And so then thing works out quite nicely. 4x squared plus 9 on 3 plus 3 on square root 4x squared plus 9. If it was a definite integral, maybe I didn't have to go back there. All right, I could have changed my limits of integration for a definite integral. Okay, so the thing is, if I have that a squared minus x squared, x is going to be equal to a sine theta. All right. But if I have sort of a squared plus x squared, I'm going to try a tan theta to turn that into a sec thing. And they have corresponding, so this is sort of the 1 plus sine squared theta is equal to cos theta. So it actually means that this is also, could be a cosine theta. And actually for sine and cos, you can use them interchangeably. All right. It's not the same way with tan, but I'm going to say, without sort of trying to do anything more about it, there are similar sort of things you can use hyperbolic functions for. So some of those things that had logs and stuff in it, they're actually involving hyperbolic trig substitution. We don't want to do that. I don't think we have to do that, and so I'm not even going to go there. All right. I'm pretty sure you do learn it somewhere, but I don't know that we have to do it now. They mention it. Yeah, so when I went through, we were expected to be able to do it, but the expectations have decreased slightly since then. Okay. So one last thing to do is to just go through and check the chat. So there was, so let's press that one and see what Hamish had actually got for me. Say, Sean. And where did it go? Yeah, okay, sure. Can we open it? Open file. That's what I want to do. Is it going to do it? Oh, there we go. What? At some point in time, the hell? All right. It doesn't want to give me these things. At some point in time. Yeah, I thought you were going to do that too. All right, I'm going to give up on that. I'm going to say thank you very much for your attention. I will have all of let's be honest, what's actually going to happen is David is going to do all the putting of stuff online. I forgot to do that. But thank you for your attention. Actually, having questions and comments makes my life easier. So good luck with the exams. Maths Learning Centre, open 10 a.m. to 4 p.m. until the beginning of the exam period. All right. So during the exam, from the beginning of exams, we are open 1 to 4. All right. So we're still open, but in the afternoons. Because I'm going to be honest, people aren't going to come in. Nobody's going to come because I don't know when your exam is, but I believe it's quite early on in the exam period. Yep. So important, check your exam timetables. That's your responsibility. All right. I do not know when your exam is. I do not intend to find out. But remember, remain calm. Write down what you are seeing. All right. And if you do not know how to answer a question, but you do know what the first thing you would do is, do the first thing. All right. That is the best thing you can do. Because sometimes the second thing becomes obvious after you've written the first thing. And the third thing becomes obvious after you've written the second thing. And suddenly you've got an answer where you didn't think you could get one. All right. So a little bit of self-belief. And I'm sure the fact that you're here means you're going to do quite well. Thanks, guys.